Alrighty guys, here's our last video for this section, and it's going to be 6.2 on inverses, which I spelled wrong. Let me throw in an S there. And determinants of a 2x2 matrix. So last time in the video I went over how to find the inverse of a 2x2 by hand using our kind of solving a system of equations method. Now we're going to use a shorter way, which uses what we call determinant, and we'll see how this works out. Alrighty guys, so you can flip to, this is the third page of your packet, and it's right after our last video. You can see the title is Inverse and Determinant of a 2x2 Matrix. So, using that system we used last time, and I think the book goes through proof for why this works, if you're curious, every time we use Gaussian elimination to solve, we're kind of going to go through the same thing. We're going to multiply by the A and C coefficients, right, one negative, so we can use that elimination method and cancel one out. And then this similar for B and D. So every time if we use a set formula for that, it's going to be this AD minus CB over here. Right, and that part you can see down here, they say that number is called the determinant of a 2x2 matrix. Now this method here only works for 2x2s, again, because it follows Gaussian elimination. After that, for 3x3s and up, it gets a little more complicated, so we'd have to go back to that Gaussian elimination method. But it's really nice for these 2x2 matrices, really quick to find an inverse using this method by hand. So, to find an inverse, it needs to have this determinant, right? Can't be equal to 0, because we're going to use that determinant in this formula that I show right below. So 1 over AD minus CB, that's 1 over your determinant, times this matrix. So you kind of switch our diagonals, switch A and D, and make B and C negative. Alright, and that'll be it. You multiply those, and that's your inverse matrix. So a couple ways they can write out the determinant. If they want us to find it, they can just write determinant A. These bars right here, so almost like an absolute value, that means find the determinant. Same thing here. Notice that instead of the brackets, right, a normal matrix has, it's just two straight bars. Again, they look like absolute value, but for matrices, that means find the determinant. So take AD, your first diagonal, and subtract CB, your second diagonal. Alright, so for A, B, and C here, you're just using that formula up above to find our inverse matrix. So I'll write out the first one with you if you want to follow along, and then I'll just put the answers for B and C for you guys to go through and check your work. So for the first one, to find our A inverse, we're going to set up our fraction. We have 1 over A times D, which is our 2 times 4, plus, or really here it works out to be a plus, right? It's normally a negative, as we can see up top in our formula, but we have negative 3 times 4, so that's going to be plus our 12. And then we have this modified matrix, so we're switching our first diagonal, 4 and the 2, and changing the sign of the other one. So I put the 3, and we'll have a negative 4 down here. Alright, and all that we have left to do is simplify. So my fraction becomes 1 over, I think we have our 20 there. And we're just going to multiply this by those values in our matrix. So my inverse matrix of A would work out to be 4 over 20, which is our 1/5, 3 over 20, negative 1/5, and 1/10. Alright, that's all that's to it for finding the determinant of a 2x2. You could definitely check this in your calculator, or like we said before, just multiply this matrix times the original matrix to make sure you get the identity, to make sure they work out. Alright, so now give this video a pause, try out B and C, and then start playing again when you want to check your answers. Alright guys, so if you try these out, letter B should have kind of worked out a little strange, right? When you actually go to find the determinant there, you get 36 minus 36 for your diagonals. So the determinant equals 0, which means we can't find an inverse, right? So matrix A, or B in this case, would be singular. Right? So as soon as you find that determinant, and determinant to be determinant, get it? Determinant to be 0. That's the peanut gallery in the car. It'll work out to be a singular matrix. Alright, so C works out fine though. You get a couple fractions. Again, you can check that by multiplying it by that original matrix.